There is no sound where it is, no light that matters, no warmth, no reference point in any direction. Just a signal traveling at the speed of light, taking nearly a full day to arrive, and another full day to hear anything back. One exchange, 45 hours. Whatever is out there has traveled so far beyond everything we know that the numbers scientists use to describe its location stop feeling like distance and start feeling like an argument against comprehension. We gave it a name, but the name is not the important part. The important part is what is happening to it right now, quietly, layer by layer, and why every solution ever reached for has created a new version of the same problem it was trying to solve. That process started the moment it launched, and it has never stopped. So you assume this was built to handle what came next. It was not. The year is 1977. The computers guiding this spacecraft process data at roughly 8,000 instructions per second. Your phone executes billions. The onboard memory is measured in kilobytes. Not megabytes, not gigabytes, kilobytes. Not enough storage to hold a single modern photograph. The entire mission relies on magnetic tape to record data, a technology already becoming obsolete on Earth at the moment of launch. And yet this machine was pointed at the outer solar system with a single instruction: leave. Not orbit, not return, leave. So it seems like engineering was the central challenge. Get it off the ground, survive Jupiter, survive Saturn. After that, the hard work is finished. But that assumption collapses the moment you follow it forward in time. Surviving the launch was never the real constraint. Surviving Jupiter's radiation belts was never the real constraint. Those problems had engineering solutions, and the solutions worked. The constraint was always what came after, when the distance grew large enough that no solution could arrive in time, when the spacecraft was left to manage every failure entirely on its own, when the gap between a problem occurring and a response reaching it stretched from minutes to hours to nearly 2 full days. Before that reality became unavoidable, both spacecraft carried something else. Attached to the body of each one, a 12-inch gold-plated copper disc, a record. Curated under the direction of astronomer Carl Sagan, it holds the sounds of Earth. Greetings in 55 human languages, the crash of ocean waves, a mother's first words to her newborn child, the low resonant songs of humpback whales, music from dozens of human cultures, the encoded brainwaves of a young woman experiencing love. The record was designed to survive for 1 billion years in the vacuum of space. But here is what that design assumes. It assumes something will find it. Nothing has to. There is no address on it, no return signal, no broadcast identifying its location. It is a message placed inside a machine, moving away from every known civilization at 37,900 miles per hour, into a region of space where the nearest star is still over 4 light-years away. It does not assume rescue, it assumes disappearance. That framing matters, because everything that follows operates on the same logic. And what happened next did not make that logic feel less accurate. It confirmed it. So it seems like the plan was straightforward. Use planetary gravity to accelerate both spacecraft outward, collect data, let them fly. But succeeding at the plan immediately created a problem the plan had not accounted for. When Voyager 1 reached Saturn, NASA made a deliberate choice: redirect it toward Titan, Saturn's largest moon and the only moon in our solar system with a thick nitrogen-rich atmosphere. Scientists needed that data. The flyby was authorized. The trajectory was adjusted. Titan's gravity did not gently assist the approach. It grabbed the spacecraft and threw it violently upward out of the plane of the solar system. Not slightly off course, completely out of the ecliptic. No further planetary flybys were possible. No correction could undo it. The trajectory was now fixed by physics, not by mission planning. Voyager 1 was leaving the solar system on a timetable it did not choose, so it seems like at least the second spacecraft could continue the original mission. And it did. Voyager 2 reached Uranus in 1986 and Neptune in 1989, becoming the only human-made object ever to visit both ice giants. It discovered active geysers on Neptune's moon Triton, erupting nitrogen gas into space in a world so cold that nitrogen itself falls as snow. But continuing the mission created a different version of the same problem. Neptune's gravity did to Voyager 2 exactly what Titan's gravity had done to its twin. It threw it downward out of the solar system plane in the opposite direction, violently, permanently. They were built identically. They launched 16 days apart. They carried the same records, the same instruments, the same onboard computers, running the same software. And the outer solar system separated them so completely that they now travel in opposite directions across interstellar space. The distance between them increases every second. No force in the universe will bring them near each other again. One toward the cosmic north, one toward the cosmic south. For decades after the separation, both spacecraft flew within the partial protection of the heliosphere. The vast magnetic bubble generated by our sun's solar wind deflects the most lethal radiation in the galaxy. Cosmic rays from supernova remnants, from neutron stars, from the violent deaths of massive stars scattered across the Milky Way. The heliosphere pushed back against all of it. Outside the heliosphere, nothing does. Both spacecraft were heading for that edge. And what waited on the other side did not make the situation feel more survivable. When they crossed that boundary, the data they returned did not confirm safety. It removed the last assumption that safety was possible, and the previous framing stopped working. The assumption was that crossing into interstellar space was the achievement. The destination was reached. The difficult part finished. The correction, crossing the heliopause, did not reduce what the spacecraft now faces. It removed the final layer of partial protection and placed both machines directly inside the environment that had always been the real threat. Voyager 1 crossed in 2012. Instruments recorded the transition precisely. The solar wind stopped. The density of charged particles shifted. The magnetic field orientation changed. The spacecraft entered the interstellar medium, the ancient material drifting between stellar systems, seeded with high-energy cosmic ray particles generated by stellar explosions hundreds of light-years away. The ambient temperature of that environment is approximately 2.7 Kelvin, negative 518 degrees Fahrenheit, 3 Kelvin above absolute zero. The coldest temperature the laws of physics permit to exist. This is not cold the way Earth experiences cold. There is no reference point for it in human experience. It is the baseline thermal state of the universe itself. The temperature of the space between stars, largely unchanged since shortly after the Big Bang. Every component on board Voyager 1 has a minimum operating temperature. Below those thresholds, materials contract beyond engineering tolerances, lubricants freeze solid, circuits fail to conduct. The thruster fuel lines, the attitude control system, the radio transmitter, the onboard computers, all of them require active heating to remain functional. The only source of that heat is the spacecraft's own decaying nuclear batteries. The implication compounds from there, because the environment is not trying to destroy the spacecraft quickly. It is slowly removing the margin for survival, degree by degree, watt by watt, year by year. There is no single catastrophic event to point to. There is only the continuous, gradual narrowing of what remains possible. And that narrowing has a specific structure, because every attempt to manage it generates a new version of the same problem one level deeper. Because the power is not simply running low, it is running low in a way where each solution accelerates the conditions for the next failure. Plutonium-238 decays with a half-life of 87.7 years. The power output drops not because something broke, not because of an external event, but because radioactive decay requires it. By 2025, both spacecraft generate roughly 40% less electricity than at launch. The number decreases every year without exception. It cannot be supplemented from outside. It cannot be slowed. It cannot be reversed. So the assumption is, turn off instruments, reduce power demand, preserve what remains for critical systems. That is exactly what NASA has done for years. Instruments have been shut down, one by one, each shutdown recovering a few watts, each recovery extending the mission by months. But turning off instruments removes data. And removing data means less visibility into the spacecraft's own condition, less warning before something fails, less ability to distinguish a minor anomaly from the beginning of a permanent cascade. So you keep only the most critical systems running, but those critical systems still require precise heat management in an environment that pulls warmth away from the spacecraft continuously. The internal temperature must stay within a specific range, warm enough to prevent fuel line failure, stable enough to keep the electronics functional. Managing that balance requires power that decreases every year. So you reduce heating output to extend the power budget. But reducing heating brings the internal temperature closer to the threshold where thruster fuel lines begin to fail. If those lines freeze, the spacecraft cannot fire its thrusters. If it cannot fire its thrusters, it cannot maintain the precise orientation required to keep its high-gain antenna pointed toward Earth. And a spacecraft that cannot maintain antenna orientation cannot receive commands. A spacecraft that cannot receive commands cannot be corrected. So turning off instruments to save power makes the spacecraft harder to monitor. Making it harder to monitor reduces warning time before a critical failure occurs. Reducing heating to compensate for power loss increases the probability of exactly that failure. And a critical failure at this distance may not be identified until it has already become permanent. Each layer of management eliminates options for the next layer. The structure does not loosen over time, it tightens. And then in late 2023, the structure produced something that had no immediate explanation and no fast solution. Something that required 45 hours just to begin diagnosing. And at that distance, 45 hours is not an inconvenience. It is the difference between a recoverable problem and something that cannot be walked back from. Voyager 1 stopped making sense. Not a weak signal, not standard data corruption. A repeating stream of meaningless binary output, matching no valid telemetry format, cycling continuously, transmitted across 14.9 billion miles to engineers in California who stared at the incoming data and could not immediately determine what had failed or how severe it was. The suspected cause, a single memory chip inside the flight data system computer, had been damaged. Not by a collision, not by a sudden radiation event. By 46 years of continuous exposure to cosmic rays and the thermal stress of operating at temperatures approaching absolute zero. The chip held a portion of the software responsible for packaging and transmitting both science and engineering data. That section was no longer functioning, so it seems like the repair path is clear. Identify the damaged section, send a corrective command, restore normal operation. But repairing the chip was not possible. The damage was physical. No software command could undo it. So the team sends a diagnostic command to understand the full extent of the problem. That command travels at the speed of light. It takes 22.5 hours to arrive, then 22.5 hours to receive any response. And here is the part that is genuinely difficult to sit with. By the time a problem registers on screens in California, it is already nearly 2 full days old. Whatever occurred on board happened, continued happening, and ran uncorrected, while engineers on Earth were still in the process of learning it existed. At that distance, 2 days is the difference between a recoverable problem and a permanent failure, between an anomaly and a loss of contact that has no resolution. The speed of light is not a technical limitation that better engineering could eventually solve. It is a physical constant. It cannot be negotiated with. For weeks, teams sent commands and waited in 45-hour silences, not knowing whether each attempt had worked, not knowing whether the spacecraft was stabilizing or degrading further, not knowing whether the next response would be coherent data or more meaningless output or silence. There was no way to know faster. That was the entire problem. The eventual solution required something unprecedented. Engineers could not repair the corrupted memory in place, so they divided the damaged software into fragments, identified separate sections of available memory distributed across the computer, and rebuilt the flight data system remotely in pieces, scattered across different memory locations, no longer where it was designed to reside, but functional. Every step of that process was transmitted across interstellar space, one 45-hour exchange at a time over the course of months. It worked. Coherent data returned in 2024. But the nature of the repair does not suggest the underlying problem is resolved. It suggests the problem has been managed one more time, using memory that is itself 47 years old. In a spacecraft that has exhausted most of its redundancies, in an environment that has not stopped doing what it has always been doing to every component on board. The next failure will have fewer available responses, and the one after that, fewer still. Sometime in the next few years, the power output of Voyager 1's nuclear batteries will fall below a specific threshold, not below the ability to run science instruments. That point was already passed years ago. Below the ability to simultaneously power the transmitter and maintain the minimum internal heating required to keep the spacecraft physically intact. NASA will face a decision that is not meaningfully a decision. Heating must be maintained, or the spacecraft fails immediately and completely. The transmitter requires power that heating now needs. There is no third option, no reserve, no backup power source that can be activated. The transmitter will go silent, not because of catastrophic failure, not because of a collision or a radiation event, because there is no longer enough power to push a signal across 14.9 billion miles of interstellar space to an antenna on Earth. From Earth, it will be indistinguishable from any other loss of contact. The spacecraft will stop responding. And at that distance, when something stops responding, there is no method of determining why. The spacecraft will keep moving. At 37,900 miles per hour, with no engine firing and no guidance correction possible, Voyager 1 will continue outward indefinitely. The golden record is still attached. The damaged memory chip is still inside. The 47-year-old circuit is still present, all of it drifting cold and silent through interstellar space with no destination and no arrival. In roughly 40,000 years, it will pass within 1.6 light-years of a dim red dwarf star called Gliese 445. Not close enough to be captured by its gravity. Not close enough to be detected by anything we currently know exists in that system. Just a machine passing through the vicinity of a star that has no reason to register its presence. In 300,000 years, Voyager 2 will drift past Sirius, the brightest star visible from Earth. A star our species has watched, named, and navigated by for thousands of years. Voyager 2 will pass near it without slowing, without orbiting, a silent object crossing that region of space at a speed no civilization there could intercept, even if one existed and was watching. Billions of years from now, our sun will exhaust its hydrogen fuel. It will expand into a red giant, its outer layers consuming Mercury, Venus, and Earth. The oceans will evaporate. The surface will melt. The atmosphere will be stripped away. Every structure ever built, every record ever kept, every artifact of human civilization will be absorbed or scattered. The two spacecraft will still be out there, in the vacuum between stellar systems, with no atmosphere to cause corrosion, no liquid water, no biological or chemical process of any kind. The gold-plated copper records will remain structurally intact on timescales that exceed the current age of the universe. They will carry a mother's voice into a time when the star that launched them no longer exists. They will carry the recorded neural activity of a person feeling love past stellar systems that have not yet finished forming. They are the most distant objects humanity has ever built. They are the last physical evidence that we existed at all. And this is what the whole story was actually about. Not the distance. Distance was always going to increase. That was the design from the beginning. The real problem is what distance does to everything else. It does something to power, makes every watt irreplaceable, makes every year of decay a permanent reduction in what remains possible, makes the gap between current capability and minimum requirement one that closes in only one direction. It does something to communicate, converts every exchange into a 45-hour commitment, converts every diagnostic into a multi-day waiting period with no guarantee the spacecraft will be in the same condition at the end of the wait as it was at the beginning, converts every repair attempt into an act of transmission across a void that does not care whether the message arrives in time. It does something to the ability to intervene, which is to say, it removes it, not gradually, structurally. The moment Voyager 1 crossed the heliopause in 2012, the category of problems that could be physically addressed ceased to exist. Everything since has been remote management of a machine, operating beyond any possibility of hands-on repair, in an environment no human instrument had ever directly sampled, using power that decreases every year, and memory that degrades every year, and components designed to last 5 years that have now lasted nearly 10 times that. The mission does not end when the transmitter goes silent. It continues, silently, indefinitely, carrying everything it was built with into a galaxy that has approximately 100,000 light-years of width left to cross before the spacecraft approaches anything else at all. The signal is still arriving. For a little while longer, it is still arriving. And when it stops, There will be no way to tell whether Voyager 1 failed, or simply no longer has the ability to answer.